We'll wait for 2 more minutes. After that, we'll start. Okay, so let us start. Today, we'll discuss the contents of week 5 of the course, and this is a continuation of the transmission electron microscopy related content that was covered in week 4. So, as usual, we'll start with recap of the topics. We'll spend some time on it and discuss if there are some doubts related to the content. After that, we'll keep around 20 to 30 minutes for discussion on the assignment. Right, 30 minutes should be good. Before I start with the recap of the content, are there any doubts related to maybe the previous assignment or the previous week's content? If there is any doubt, you can unmute and ask me. I have also prepared some questions for week 5 course content also. So it is advisable that after the doubt solving session, you go to these questions and try to answer them. If there are any doubts, any of you have regarding TEM, which was the basics of TEM, which was covered in the previous week, you can ask now. In the previous week, Sir had covered Monte Carlo simulations so that you can get to know the all possible trajectories of the electrons once it interacts with the material. And this is relevant for SEM because there you have bigger samples. So you want to know the interaction volume that is uh, present in the sample where the interaction of incoming electron and the material happens. Then after that, Sir had started TEM, where we understood the different components of TM, their functionings, like their basic functionalities, And then we understood how image formation happens and how we are able to generate a contrast in the TM images. Then we looked at the two different modes of imaging, bright and dark field. And after that, we covered some different contrasts. So mass thickness to contrast. I think phase contrast was also covered. Diffraction contrast. Now we'll continue with this. So firstly, just let's take another look at, at image formation in case of TM. So it had been told that we have a lens arrangement as it is in any microscope. So we have a particular arrangement of lenses for TM. But here um, you can just assume that because many of these lenses, for example, this projection lens system, its function is just to enlarge the image. So if you just so if you just assume that uh, the electron beam is coming from the specimen, it is taking some path and then reaching the screen. And if we know the angle 2 theta, if the angle of diffraction is 2 theta, and we try to measure what is the distance between the diffracted beam when it reaches the screen and the direct beam, and call it small r, then what will happen is this r, small r divided by L, where L is the distance between the object and the specimen. It's not the physical distance because you have many lenses in between, but you can consider L to be here it has been called camera length. So this will be different from the physical different distance because it will also have to incorporate the refractive indices of the lenses. But you can call it the notional length. So the length that the electron sees as it comes between it, as it leaves the specimen and reaches the screen. Let's call it camera length and write it as capital L. And if small r is the distance of the refracted beam from the object, then small r by L is tan 2 theta, which is about approximately 2 theta because theta angle is very small in case of TEM. And then you can also get a theta value relationship from the Bragg's law, which establishes the relationship between the wavelength of electron and the interplanar spacing in the crystal. And if you equate these two, then what we get is L lambda equal to RD. And because capital L, which is the distance between the specimen and the screen, the notional distance, as well as lambda, both are constant for the instrument. So we know that L lambda is constant, and as a result, small r into small d, that will also have to be constant. So we can say that the distance or the distance we get from the screen is proportional to inversely proportional to the interplanar spacing in the crystal. And this is actually very important because this is the basis of getting to know the interplanar spacing in the crystal which you are investigating using TM. And by measuring the distance of the direct beam from the diffracted beam, you can get the value of small d, and from this you can get information related to the both the orientation of your material by knowing what is the plane that is diffracting, as well as the uh, uh, atomic spacing between the atoms in your material, right? So because of this, camera constant is important. Now we'll come to another important idea when it comes to learning about TM. It's also one of the building blocks that you will need to understand, so that you can understand many of the concepts related to interpretation of diffraction pattern in TM. And this concept is reciprocal lattice. So till now we had understood diffraction from the Bragg's law perspective, from what we call the real space. But here we'll look at something called reciprocal space. And this is a hypothetical space. Give me a minute. Yeah, this is a hypothetical system that we'll use, but this is very much useful when you are working on TM related diffraction patterns. So the basic uh, concept of reciprocal lattice is that uh, here each plane is represented by a point, and this point will lie at a distance of 1 by small d from the origin, which is where the direct beam hits the screen. And it will be the perpendicular to the plane, and this distance 1 by d will be perpendicular to the plane from which diffraction happens, right? So just to very in just to give us small idea of it, if this is your origin, and here is a diffraction spot, then this distance distance will be 1 by d, proportional to 1 by d, and your plane from which diffraction happened will be perpendicular to this, right? And this can be considered the spacing that you have in the reciprocal lattice for this plane. And this vector, which describes the position of this reciprocal lattice point for this plane, is called the G vector or the diffraction vector. Give me a minute. Understanding reciprocal lattice is quite important. So if you have any doubts, you can ask now, or also try to look through some uh, proper content from any TM related book or X-ray diffraction related book to understand even in much better detail. Just a second, I'll continue. Yeah. Okay. So now we got some brief understanding of how we can represent a plane in this system, which we call the reciprocal space or reciprocal lattice. So what we normally use, or how, or the way in which we used to visualize atoms till now, was in the real space where you have a lattice which is kind of a grid, and in that lattice you have atoms sitting on the lattice points, and that was your real space. But here we are talking about a different space which is called reciprocal space, and there also you have a lattice, and each point on the lattice corresponds to a plane in the real space. I won't go through all the lines in the presentation. And so every plane has a corresponding diffraction vector or reciprocal vector in the reciprocal lattice or reciprocal space. So there you can do a one-to-one mapping between the real space and the reciprocal space. For example, if you have this normal to a plane A, then in the reciprocal lattice, the same plane can be represented by a point, and the spacing and it can be called as A star with respect to the origin. And just like we have a three-dimensional real lattice, you also have a three-dimensional reciprocal lattice, and each point corresponds to a plane in the real space. Now we know that in TM we have um in the let's say parallel electron beam mode, when you have a parallel beam of electron, the angle theta by which diffraction happens is very small, typically always less than 1 degree, much smaller than 1 degree. So you can say that all the planes which will diffract will be almost parallel to the electron beam. And as we saw from the camera constant derivation, that okay, so in the camera constant derivation, we saw that in the diffraction pattern, the distance of the diffracted the diffraction spots from the central beam will be proportional to 1 by d, right? And to be precise, it will be L lambda by d. So you can say, since the the distance is proportional to 1 by d, we can say that this diffraction pattern is a scaled version of the reciprocal lattice, and this lattice is normal to the electron beam, and the scaling factor is L lambda, right? We can say this because we know that in the reciprocal space, in the reciprocal lattice, the diffraction vector of any plane will have a magnitude of 1 by d, and if we scale it use by multiplying with L lambda, what you will get will be the same as the diffraction pattern you are getting in TM. I hope this is a bit clear. Also, Another way of putting the same thing is that if you have a crystal oriented in a particular way, and if you take a section of it, uh, if you have a crystal oriented in a particular way and you bring it to the reciprocal space, so you have a reciprocal lattice and you take a section of it, then the all the points that you will see on that section, all those reciprocal lattice points, they will look the same as what that crystal will look if you put it in TM and look at the diffraction pattern, right? So in this way you can make a correspondence or of the diffraction pattern you get in TM to the reciprocal lattice of the crystal which you are investigating. So it's written, the same thing is written here. These slides are quite good. You maybe if you just follow these slides it will be difficult, but if you follow the lectures of sir and then you come to these slides for revision, then I think you should be pretty, you should find this pretty easy to understand. Also, if you have understood this part of it, all these basic building blocks of reciprocal lattice camera constant, then understanding the uh, rest of the material, which is concerned with indexing of the crystals of the diffraction pattern, then finding the composition of or the structure of the material, that part will be much easier if you have understood all this. Now let's to come to another concept which is of eval sphere. So this establishes a relationship between the reciprocal lattice and the diffraction pattern. Here the diffracting crystal is represented by its reciprocal lattice, and the new thing here is that the electron beam which is incoming is represented by a vector of length 1 by lambda parallel to the beam direction, and this terminates at the origin of the reciprocal lattice. Now if using this vector of length 1 by lambda you make a sphere, then what you will find is that if it is touching a diffractions, if it is touching a reciprocal lattice having a diffraction vector of g, then in that case if the sphere touches this reciprocal lattice point, then it means that diffraction will take place for this plane. This plane will refract the electron beam, and you can also put this as being a condition for diffraction to occur. How we uh, how we can say this, or how we can derive this, is something like this. So we have already looked at camera constant, right? R by D equal to R by L equal to 2 theta, which is equal to lambda by D. So RD by L, so 1 by lambda can be written as L by RD, Or okay, sorry for confusing you all. We can simply see that if this is the case here for this sphere, then 1 by lambda into, if theta is very small, then 1 by lambda, which is the radius, into 2 theta will approximately be equal to the g magnitude of g vector, which is 1 by d. And if this is happening, if the sphere is getting intercepted by any reciprocal lattice point, then this will be true. And if this is true, then this is a condition for diffraction to happen, right? As we saw by using Bragg's law, this is the condition of Bragg's law. And so you can say that if this sphere of radius 1 by lambda is touching any diffraction, is touching any point on the reciprocal lattice, then for that point diffraction will occur. And usually the angle theta are very small due to the high energy of electrons that we are using. And because of this, we can consider this thing, this sphere touching the reciprocal lattice point, as being almost a plane, because this angle is very small, so it can be considered as just one plane. And because it is like a plane, there will be multiple spots like this which the sphere usually touches, and we'll be seeing multiple points that the sphere will be touching, and we'll be seeing them as diffraction spots in our diffraction pattern. Now we'll move to understanding what will happen uh, if the thickness of the crystal that we are seeing is changing. Mm. We now know that if we have a reciprocal lattice for a crystal and we have this sphere, then diffraction will only occur if the sphere touches the reciprocal lattice points. But in case the crystal is thin, then in that case, even if you're slightly away from a point, let's say by this value s, by this vector s, even then diffraction can, you can get a diffraction spot for this point, diffraction can occur. I won't go, because in this lecture sir has not gone into explaining the reason why this kind of phenomena happens for thin crystals. Why, if you have a thin crystal, even if the sphere is not touching a spot, you can, if it is close enough, you can get diffraction spot for that point. But so I won't go into the derivation of that. But you should know that if you have thin crystals, because of this you will see much more number of spots on the diffraction pattern. Mm. So if you have a incoming electron beam and it is getting diffracted from different planes of the specimen, then if you add all the contributions from each of these scatterings, from all of these parallel planes, then you will get intensity which will be something like this. So you will get one main peak which will be at the Bragg diffraction angle, but the width of this peak will be proportional to 1 by the thickness of the crystal. If the thickness is small, the width of this peak will be larger. So what this will mean is that even if theta is a bit different, if there is some delta theta equal to theta Bragg minus the actual theta that is present at which diffraction is happening. So even if there is some difference, if some delta theta is there, if thickness is small, the width of this will be large. So you will be able to see diffraction occurring even if the plane is not exactly at Bragg's angle. This is a equation or formula which tells you the intensity of scattering from a crystal. If you have uh, thickness T, and I think this is S is the S is this value, the difference between the reciprocal lattice point and the sphere. But the major takeaway of this slide is that if you have a thin crystal, then you will get more diffraction spots, because even if the sphere is not exactly touching the reciprocal lattice points, due to this phenomena of broadening of this thing, you will still be able to see some peaks. So even if theta is a bit different from Bragg angle, still diffraction spots will be visible. So one way of visualizing this phenomena is by seeing the reciprocal lattice points as now extended in a direction normal to the plane of the specimen. So now, since we have these things we can call rail rods instead of points, if the sphere intersects these rods, then still we'll see a diffraction pattern. In this image we can see that this is from the thinnest portion of the crystal and this is from the thickest portion. In the thinner one we can see multiple diffraction spots, while in the thicker one we see less number of diffraction spots due to this phenomena only. And because of this phenomena, since diffraction is this diffraction spots are visible even if there is some change in the angle theta, there some delta theta exists. Because of this, it will be difficult to know the exact orientation of the crystal which we are investigating. So there are some other techniques which can be used to get this information about orientation of the crystal. Another phenomena which occurs is when you have a plate like crystal which is oriented parallel to the beam. In this case also the reciprocal lattice points get extended perpendicular to the beam in a similar fashion. And in this case there are streaks which can be observed in the diffraction pattern. So if this all is understood, now we'll go to using all these basic concepts we learned about reciprocal space, evolved sphere, and the camera constant at the different diffraction patterns and how they'll change for crystals and polycrystals. In case we have a single crystal, which means there is a fixed orientation of all the planes. So there is a fixed orientation of all the planes, and because of this, the diffraction pattern that you will get will be very clear, something like this. We'll have multiple spots corresponding to all the planes which are undergoing diffraction. And as we know that in our diffraction pattern, the distance of the diffraction spot from the center is proportional to 1 by interplanar spacing. So as we go uh, so we can say that if the interplanar spacing is much smaller, then you'll be seeing diffraction spots which are much away from the center or much away from the direct beam. And so we can, let's say for uh, this particular diffraction pattern, if this is 111 bar uh, diffraction spot, then similarly if we keep going ahead, then this will become 222 bar, then you will have 333 bar. And if you calculate small d values, then these small d will be smaller for this plane and even smaller for this one. So in real life we rarely have single crystals. We have sometimes single crystals in gemstones and some natural mineral formations, but it is very but most of the mm, materials will we deal with are polycrystals. So there are very small crystals, crystals or grains, and there we have lots of them in our material, and that is why we call it a polycrystal. And if we do TM of a polycrystal specimen, instead of seeing clear diffraction spots, what we'll observe will be rings of this kind. And this happens because since this happens since we have multiple grains or multiple different crystals. So grain can be considered as equivalent of a crystal. It's you can crudely say that grain is equivalent of a crystal. And since you have these multiple crystals, and of them have their the same have planes oriented in different ways. So same plane in one crystal may be oriented in a way which is different from that in another crystal. So because of this, we get this ring like pattern, and each ring here will correspond to one plane. But because you have different crystals, the points on the ring will be all situated on a circle. And each of this ring will have a radius which will be proportional to 1 by small d, where d is the interplanar spacing of the lattice plane, due to due to which these uh, rings are forming. So for each diffracting plane, we'll have one ring. And this can also be understood using this schematic. So the same plane is oriented differently in each crystal due to the different crystal orientation. And but since the plane is the same, that is the spacing between the planes is also the same, the theta values will not change. It's just that it will get rotated. So for one particular theta, you'll have a whole circle that you'll be able to that will form on the screen, and this circle will correspond to the lattice plane from which diffraction is angle happening at an angle of 2 theta, and as a result we get these rings. Here we see that we have 5 images. The fifth one corresponds to almost a single crystal, that is epitaxial growth, that is a textured growth of single crystal growth. And the first one corresponds to a random polycrystal where you almost have 100% randomness. So you are seeing uniform rings. Now we'll come a bit more towards the operation of TM, something related to the operation mm, and the arrangement of the some of the components of TM. Here we'll discuss about selected area diffraction. Till now we had been not talking about what all portion of the specimen the electron beam interacts with, and since diffraction will occur at all of the portions of the specimen where the electron interacts, you will get information from all of these together. For example, in a polycrystal you get information of all the crystals, and as a result you are getting these rings. But it is also possible to be to selectively choose a region in your specimen from which you want information through diffraction patterns. And this um, process of choosing your region of interest is called selected area diffraction. So you are selecting a region here and then looking at the diffraction pattern. So how is this selection of region carried out in case of a TM? As we know, we have a specimen which is just above the objective lens and below the condenser lens and condenser aperture. So even this just a small uh, piece of information that even the objective lens here is not just a single lens. There are I think upper pole piece and a lower pole piece, but here just for simplicity we are showing as a single lens. So if you have the specimen setting here, then what we can do is that we can put a thin strip of metal to block the beam such that only the beam will only pass through your region of interest in the specimen. So this can be done by putting a thin strip or an aperture either at the specimen, just above or below the specimen, or at the image plane. So, so we can put the aperture in the image plane, and from that we can select the area of interest we have in our specimen and get information related to that only. So in case we have a polycrystal TM specimen, then we can just choose one specific grain we want to investigate and put a SAD aperture on that grain, and then analyze the diffraction pattern we are getting. This technique, SAD, can be used to identify crystal structures by analyzing the diffraction pattern, and also examine crystal defects by seeing how the diffraction pattern is deviating from the ideal diffraction pattern that should occur in case you have a perfect crystal. So here, for example, in this diffraction pattern, you can see that there are spots which are not corresponding to a single crystal. So these are for this particular alloy, and there you have two phases here, and we can see spots corresponding to both of these phases, and the zone axis has been indexed as being this and this. We'll talk about what is zone axis later on. I'll try to hurry a bit. So I'll cover structure factor, after which we'll go to zone axis and indexing. I think these parts are more easier to understand if you have understood the previous stuff. So I hope that I was able to convey some of it to you. Now let's come to structure factor. So till one now we were only talking about planes in the lattice and the spacing between the planes, but we didn't really consider what um, we didn't really consider the specific positioning of the atoms, which depends on the crystal structure of the material which you are seeing. So even that the positioning of the atoms due to the crystal structure will have a effect on the diffraction pattern that you'll observe. And if we want to get the intensity of the diffracted beam from a particular lattice plane, then we'll have to add up the contributions of scattering due to each atom which makes up that plane, and also account for the phase of the wave that is scattered by each of these atoms while you are adding up their contributions. So both the amplitude and phase have to be considered here. And when you do this adding up of contributions from each atom to the intensity of the diffracted um, to the intensity of the diffracted beam, then what will happen is that many a times the sum of all these contributions from the atoms will become zero, basically due to disruptive interference happening, where when you incorporate there, where there is a phase difference of some finite value, and due to these phase differences all the wave amplitudes cancel each other, so you'll have zero sum. That is, those planes will not uh, show any diffraction spot. Even though diffraction is happening, they are in diffraction condition, but still they do not show diffraction spots. because of the kind of interference that is happening. So these are called forbidden reflections. So these planes will always be invisible from your diffraction pattern, no matter how you orient the crystal. These waves will not diffract, or I should put it better that these planes will not be visible in the diffraction pattern. And so here the exact derivation is not shown, but I'll just briefly explain what is this formula that is used to calculate. So actually this phenomena, or this adding up of the contributions for a particular crystal structure, is called the structure factor. That is the effect of the structure of the crystal or material on the intensity of the diffracted beam. So one of the contributions to the intensity comes due to this structure factor. Hmm. And as I told, along with Bragg's law, structure factor also has a say in um, how the diffraction pattern will be. And now let's come to what is this formula written here. We can write the structure factor for a particular plane as being equal to sigma small fi, which is dependent on, this is a constant, you can say, for a particular atom. So this I can't recall the exact term to the exact term for this for the smallest variable, but this tells you uh, how much of scattering is happening for a particular atom, and it will differ for different atoms because the electronic structures of different atoms are different. So if you have just a one, so if you add up the small f values into e raised to 2 pi I into hx plus ky plus lz, where hkl is the plane for which you are trying to get the structure factor, that is the contribution of the this plane to the diffraction. So hkl is your plane of interest, and xyz are the positions of the atoms in your unit cell. So if you make this calculation of adding up small f into e raised to 2 pi I into hx plus ky plus lz for the different positions of the atoms in the unit cell, then what you get is called the structure factor. And I won't do the calculation, but if you uh, consider FCC crystal, we know that in an FCC crystal, the atoms sit at the face center, right? So, so the position of the atoms, if small a is the atomic, is the lattice parameter, then the position of the atoms will be A by 2 110, A by 2 101, and A by 2 011. So corresponding to this, there also there will be atom at the origin, that is 000, and by repeating this, by repeating these atomic positions, we can form the whole of the lattice just by adding up all of these. And I hope I am clear. So since these are the most elementary positions of the atoms, we'll consider these, and there will be one term corresponding to each of these positions. So you have a 0, a by 2 into x plus y, a by 2 into y plus z, a by 2 into x plus z, and then you will have some you will have the have the contribution due to the HKL, the particular plane that you are considering. And if you just keep it a variable as HK and L and do this computation, what we get is the structure factor will be equal to 4f if HKL and L are all even or are all odd, and 0 if HKL are mixed. In case of BCC, we know that the atoms sit at the body center and the corners, and you can uh, you can denote this crystal structure by considering atoms at a by 2 into 111 and the origin. So if you by just using these two vectors, you can make up the whole of the BCC crystal lattice. In case of FCC, you need to have these um, three different vectors. So now if we do this computation for structure factor of BCC, we get 2f if h plus k plus l is even and 0 if h plus k plus l is odd. Now once this makes a bit of sense, we'll just consider different HKL values and see what will be the structure factor for all of them. Now if we consider only on those for which, let's consider FCC only. For BCC you can do it by yourself. So for FCC, if we start with all the HKL values which will be possible, that is starting with 100, 010, and so on till 110, 101, and so on, all the possible lattice planes, then we'll see that only when HK and L are either all even or all odd, that is unmixed, you'll have a finite value of structure factor, and only then you will see the diffraction spot for the plane. And so because of this, only these particular planes will be visible in your diffraction pattern for FCC. In case of BCC, this set of planes will be different because here the condition is h plus k plus l should be even. So we'll start with 110, then we'll go to 101 and so on. Then we'll go to 200. So the set of diffraction spots for BCC will be different, and we can calculate d by a for these planes, and from this we can get the spacing between the spots which we'll see, or the distance of the spots from the direct beam in the diffraction pattern. So we have talked about camera constant already. L is the notional distance between the specimen and the screen, and this can be calibrated by using a standard polycrystalline gold foil, for which we know the d values. Hmm. So before moving on, I like to say that TM is a pretty complicated topic, because there are lots of new concepts that you will have to intake and understand, so as to understand the whole of this thing. It's a bit more difficult compared to understanding SEM. So I'll suggest that you all go through the video lectures. Just going through the slides or going through my recap of the topics might not be enough. It will not be enough to be able to get a good grasp of TM. Moving on. So we have talked about the crystals, effect of crystal structure on the diffraction pattern, effect of the planes which are diffracting. But now we'll try to understand what will be the set of planes which we'll observe for a particular orientation of the crystal in the specimen. What will be the set of the planes which we'll observe in the diffraction pattern, and what kind of a pattern will they form? So let's say you have a particular orientation of the crystal, and we have a parallel beam of electrons coming to the specimen, to the crystal, and diffraction is occurring. Then we know that all the planes which are oriented in a favorable manner will undergo Bragg's diffraction, and depending on the structure factor, if they are not forbidden, those planes will show diffraction spots in your diffraction pattern. And so in your diffraction pattern, we'll get all of these planes which are diffracting. But now, how can you correlate this to the orientation of the crystal which you have? To do that, we have something called zone axis, and this is basically an axis or a direction which is perpendicular. So zone axis is basically a direction, and all the planes which have their normals perpendicular to the zone axis are called planes of the same zone. For example, if you have a crystal and you have the 0, 0, 1 direction in that crystal parallel to the electron beam, then you say that the zone axis for that particular orientation of the crystal is 0, 0, 1, and all the planes which have their normals perpendicular to the zone axis, which is 0, 0, 1 here, will be called planes of this 0, 0, 1 zone. So in this case, we have 1, 0, 0, 2, 1, 0, 1 bar 1, 0. All of these planes are parallel to the zone, or their normals are, or we can also say that the normals are perpendicular to the zone, and as a result, they are planes of 0, 0, 1 zone axis. So this is the definition of zone axis, and we know that for planes to be able to diffract, they need to be almost parallel to the electron beam. In other words, they need to belong to the zone axis, which is parallel to the electron beam. And when you are actually doing TM, actually to be able to really get a sense of these diffraction patterns and correlate them with the uh, lattice planes in the crystal or the arrangement of atoms in the crystal, you need to have some TM operation experience, so that you can also understand the effect of the lens arrangement and the setup of the TM on your diffraction patterns. But anyways, this can give you a preliminary idea about TM, and maybe later on you can apply it to when you are operating a TM or working with the information that you get from TM. So in when you are doing a TM, you will get these kinds of images, and each of these we can see this kind of mm, arrangement of, uh, you can call it lines or bands. Bands is a better term. So we have these bands which are oriented at different angles, overlapping on each other, and there are some points where they all meet each other. For example, here they are meeting together, lots of different bands, and this particular point is actually called a zone axis. So this is a 0111 zone axis, and all of these bands are actually Kikuchi bands. We will not get into what is Kikuchi band in this lecture. Probably in the upcoming weeks it will be brought up. But all of these bands are Kikuchi bands corresponding to a particular plane. And for a particular zone axis like this one, all the bands which are intersecting at this zone axis are part of the 011 plane, are part of the 011 zone axis. So you can have multiple zone axis as your crystal orientation is changing. You'll have different zone axis parallel to the electron beam, and as a result, we'll see this kind of a change in the diffraction pattern or the Kikuchi band pattern. So as you tilt the crystal, you'll be able to move from one zone axis to another. So here we have 011 zone axis. As we are tilting the crystal, such that later on the 001 zone axis is parallel to electron beam, we see this kind of image. And then as we tilt it in a different direction, we'll be able to move to a 111 zone axis. So 111 direction in the crystal lattice is parallel to the electron beam, and like this we can make a map or a Kikuchi map which can tell you about your crystal orientation. Hmm. I'll have to hurry, we are running out of time. There's still a lot to cover, I think. Yeah, so TM can also give you information related to composition when you use a EDS, X-ray spectroscopy, in combination with TM. But it can also tell you about the crystal just based on this give you information of the crystal just based on the diffraction pattern that you get from TM. And by combining the compositional information from X-ray spectroscopy as well as the diffraction information from TM, you can decipher a lot of details regarding the material which you're using, which might you might not be sure about. So if we do use a material and If we do not, we want to characterize it, that is we want to get information related to the structure of the material, the composition or the atoms that are in that material, then their arrangement in the crystal. If the material is unknown to us and we want to get this information, then once we have the diffraction pattern for that material, we'll want to know what are the planes corresponding to each of the diffraction spots. And for this we follow a process called indexing. So by understanding some of the theory of diffraction in TM, we know that this spacing is 1 by small d, right? And also these all correspond, or these are scaled version of your diffraction vector g. So this is a scaled version of the 200 g vector, 2 bar 00 g vector, and so on. And all of these, we know that for a particular lattice plane, the diffraction vector for that plane will be parallel to the normal of that plane in the real space or real lattice. So we know that the orientation, that the normal to the 2 bar 00 plane is along this direction, while to the 1 bar 1 bar, sorry, right now we don't know what is the plane that is corresponding to each of these spots, right? So for example, you have two spots. By looking at the distances, you know the values 1 by d1 and 1 by d2, let's say. So some constant, that is camera constant by d1 and camera constant by d2, you know these. Then we also know the angle theta, and we know that the diffraction vector is parallel to the normal of the plane. So by knowing this angle, we can we can know the angle that will be between the normals of the planes which are making up these two diffraction spots. So using these information of the angles as well as the d spacings, we can get some preliminary idea of what could be the family of planes these correspond to. And then based on the angle, we can tell what the particular indices may be. We fix the indice for one of the planes, and then considering that we can calculate for all the other planes based on the angle, because it doesn't matter where you axis you which direction of the axis you consider as positive or negative. You just need to fix your reference, that is what is important, and then do all your computations considering that reference. In this way we can index all the spots which we are getting from the diffraction pattern and get to know what are the planes corresponding to that spot. And once you know the planes, what is the zone axis for that particular diffraction pattern. Now what all information can we get by doing this indexing? We can measure the camera constant, which is usually calibrated using the gold foil and is constant. Then we can image in different diffraction contrast modes. I'll talk about it in the upcoming slides, so I'll not spend time here. I'll quickly go through. Then we can know lattice parameters and symmetry information of unknown material, that is structure related information. We can get the interplanar spacing, the orientation of the material, then the relationship between the different planes, or the orientation relationship between the planes. Also, we can get some defect related information, which I'll get into later. Now let's come again to dark field imaging. So this was discussed in the previous course also, previous week also. What do we already know about dark field imaging? We know how dark field imaging is carried out. Instead of allowing the directed beam to fall on the screen, we only allow the diffracted beam. So we only allow the diffracted beam to pass through, and we capture the image corresponding to this diffracted beam only. In case you use a direct beam, you will get a bright field image. You will get information based on how the transmitted beam or the incoming electrons uh, interacted with the features of the material, and how they transmitted through it. But in this case, you'll get information related to the diffraction due to the features. So that is the major difference when it comes to understanding the difference between image formed by bright field and dark field. And for doing this, we use an aperture which is kept in the back focal plane of the lens, and it's called an objective aperture because this is kept just below the objective lens in the back focal plane of the objective lens. Now, I hope this is clear, the arrangement of the aperture. And the reason this is kept in the back focal plane, I'm not sure if sir has discussed this, is that once you have a diffraction happening at an angle of 2 theta, then all the parallel diffracted beam, will pass through this objective lens, and then it will focus at a point here which will be away from the optic axis. After this, it will uh, get it will go in different directions, but it will all come through one single point. And by choosing only this point using an aperture, we are able to get information corresponding to a particular diffracted beam that is for a particular 2 theta diffraction, and that is the reason that we choose to keep the aperture in the back focal plane. Now we have, I think, seen this earlier also, that if we have this TM image, this diffraction pattern, and we choose just the direct beam, we put the objective aperture here and then try to see the image, we'll see the bright field image. If we do not put any aperture, we'll get information from both diffracted beam as well as the transmitted and scattered beam. So all of the beams will be considered by image formation, and we'll get this kind of an image. But if you want to get specific information, then you can get information corresponding to either the direct beam, that is the transmitted beam, or the diffracted beam from specific planes. So for this particular diffraction spot, you got this image. For this spot, you got this image. And we can see that the portions which were dark in the bright field image are actually bright in some of the dark field image. Dark in the bright field is brighter in the dark field, right? And this is because what this tells you is that these portions of the specimen are actually having their planes in such a manner that they are diffracting the incoming electron beam, and because of this these regions cannot be seen, are seen as dark in the transmitted in the bright field image. Similarly, this region is diffracting, has planes which are diffracting at a particular angle, and all these planes form this spot. But since they are diffracting, then they will not they'll have lesser transmission of electrons, and as a result they'll appear darker in the bright field image. Makes I hope it makes a bit of sense, and I hope now it's more clear why we are getting these kinds of different images for bright field and dark field. Now that we have understood uh, how diffraction happens and what are the multiple factors which affect the final diffraction pattern. Okay, now we'll quickly breeze through all of these slides, so we can understand phases from the SAD pattern based on the d spacings we get. We can get, because every phase has a different has a particular spacing of its lattice planes. Mhm. And it is like identification mm, mm, characteristics of each plane of each phase, that it'll have a particular spacing between the atoms in the lattice, and by knowing the d spacing we can correlate that to the uh, correlate the obtained d spacing to that which will be in case of a particular phase, and from that we can identify the phase. Now, this is also shows a Kikuchi map for TIXOY. So here you have um, this layer of TIXOY in this material, and we want to know what is the composition of it. So by capturing the image at different angles, at different orientations of the crystal, we can make this kind of a map from which we can get information related to the structure of this TXOY phase, as well as the spacing. And from this spacing, these are all like some clues that uh, so if you see a material science researcher as a detective, then these are all sources of clues to understanding what the material could be that the researcher is investigating. So he can look at these Kikuchi maps, he can get information related to d spacing, and this information he can compare with what is present in the standard database. So for it, just like in case of in case of having a detective and some criminal, you have a database of different criminals and their characteristics. Just like that, we have a database of materials and their characteristics, and we try to identify from all these information what the specific material, the phase in it, the orientation of the crystal, what they might be. So these are also all kind of case studies which are being shown. From this, the specific planes could be uh, identified from these diffraction patterns, and by looking at diffraction patterns at particular regions, it is also possible to get the orientation between the two different phases. For example, here you have omega alpha and beta phase, and by looking at this region, maybe the diffraction pattern obtained for this region, and analyzing the diffraction pattern, here it's omega and alpha, so it's this region. By analyzing this, we can get an orientation relationship information related to omega and alpha phases. These are some more diffraction patterns for different phases in this particular material. You have A phase and B phase and a matrix phase, and for each of these the diffraction pattern comes out to be different. Now we'll come to dislocations. Okay, so we'll have less time for the assignment, but it's fine. Now that I have explained all of this, the assignment is a very small subset of what all I have explained, and you all should be able to do it by yourself. I'll just tell you the answers quickly. So now let's come to understanding how we can get defect related information from the diffraction patterns. Since the crystals that we are investigating are never perfect due to different defects that are present in them. So the diffraction patterns also we observe will not be the ideal diffraction pattern. They will change slightly based on the different defects that are present in the crystal. So there are multiple defects that can be present in a crystal. There are 1D defects like point defects, 2D defects like dislocations, then three-dimensional defects like porosities or different phases of precipitates that might be forming, which are undesired. So won't go into all of these, but in case of metals, one very important defects both from a property point of view as well as from a structure point of view is dislocations, which is a 2D defect. It's a line defect, and basically, okay, I'll give you a brief overview of water dislocations. So a very simple way of understanding dislocations is looking at this particular case where you have a stacking of atoms, atomic layers, atomic planes, and there is one extra half plane here, which is called a edge dislocation actually. So if you have a extra half plane like this particular line, which goes into the paper, where you have an extra set of atoms which are not uh, bonded to any atom here. So there will be a strain just above and below this line of atoms, and this, because of this strain, this is called a dislocation line, which goes into the paper. And if we want to get information related to these dislocation lines from a TM diffraction pattern, there is a specific procedure of getting that information. I hope you now have some sense of what a dislocation is. If you are from material background, then you might already be knowing, but if you are not, then I hope that my basic description was enough to get a sense of what these are. So if you have these dislocation lines which have a corresponding strain field associated with them, then due to these lines or extra half planes in this case of edge dislocation, there will be a change in the spacing of the planes in this local area. So the d spacing will slightly change by some delta d amount, and this change in d spacing and the corresponding this change in d spacing can be observed, can be seen in the TM images Also, these dislocations have a Burgers vector associated with them, which is given by this symbol B. And if you have lattice planes having diffraction vector G, then the dislocations will be visible in your TEM image only when G dot B is not equal to 0. And the reason these dislocations are visible because of the local change in delta D in that particular area near the dislocation, due to which, for example, if we see here, there will be some diffraction taking place uh, in the some diffraction taking place at these points, or some scattering, I should say, taking place near the dislocation lines, due to which you will get some contrast both in the bright field as well as in the dark field images. So it's written here, you can read it. So because of this scattering, we'll see some contrast, and this will only be seen when this particular condition is followed, G dot B, for that dislocation, particular dislocation, and the lattice plane, diffracting lattice plane. If G dot B is 0, then we won't see the dislocation, else we'll be able to see it. So from this you can get information related to how many dislocations are there, what is the nature of the dislocations, what are their Burgers vectors, how are they arranged, as well as other defects like stacking faults, which are 2D defects. Then here also, this is I think HRTM, high resolution TM image, where you can see the specific atomic planes, specific atomic arrangement. And here also we can see that there is a small defect here in the mm, arrangement of the atoms, which is given by this blue line. So this corresponds to a dislocation having this Burgers vector. With that, the recap of week 5 content is complete. If there are any doubts, you can ask me. It was a pretty comprehensive discussion on TM. If there are no doubts, I'll open the assignment file for this week. I hope you all are, nobody is finding an issue with joining this meeting. If there is any issue, you can tell me in the forums. So let's quickly cover the questions. First question is related to camera length. What does the camera length signify? The correct answer is, it tells you about the distance between the specimen and the diffraction pattern, but it does not tell you the physical distance. It tells you the notional distance because there are lenses also present. So the distance which the electron encounters will be different due to the specifics of the lenses. So you have the correct answer is C. Second question, we have already covered this. So when you have a thinner crystal, you have railrod formation. So instead of the points in the reciprocal lattice, you can consider them as rods. And the eval sphere, if the eval sphere is sorry, if the eval sphere is cutting any of these rods, then you will see a diffraction spot corresponding to all of those points, all of those reciprocal lattice planes. So as the crystal becomes thinner, these rods will increase in length, and as a result, more of more number of lattice planes will cause diffraction, and you will have a higher number of diffraction spots in the diffraction pattern. So the correct answer is A. Now, if radius of eval sphere is 250 nanometer inverse, what will be the electron wavelength? So we know that the radius is proportional to 1 by lambda, and here it is equal to 1 by lambda, and here it is equal to 250 nanometer inverse. So if you take the inverse of this, lambda equal to 1 by 250 nanometers, which is equal to 4 by 1000. So the correct answer is 0.004 D. Question 4. Bright field TM image forms with, we know that it forms only for the direct beam. All the diffracted beam gets blocked due to the aperture, the SAD, sorry, the objective aperture. So the correct answer is B. So this is about the structure factor. The correct answer is B. It considers both the location of the atom as well as type of atom. So we know that in the structure factor equation, small f for h for a plane HCl is equal to sigma small f into e raised to 2 pi I into hx plus k ky plus lz, and xyz give information about the location of the atoms, HKL about the concerned plane for which we are seeing the structure factor, that is the contribution to intensity, and then we also have small f which gives information related to the specific atom which is causing diffraction. So type of our atom is also covered. So your correct answer is B. Next question. So I showed an image where we saw both the bright field image and the dark field image. What is it? Dark in bright field is dark in, so we know that what is dark in bright field will be bright in the dark field image, because what is dark in the bright field, I'll just repeat what I've already told. What is dark in the bright field are those features which are scattering the electron beam, scattering or diffracting it. So a diffraction is also, I think, kind of scattering only. So those areas which got scattered or diffracted will look dark in the bright field image. But if you then choose the corresponding diffracted beam only, then those features will look bright, because though all those have diffracted the beam and you can see the beam falling on the screen. So the correct answer is C. Next question. The answer is scattered electrons. The center spot is formed by scattered electrons, which are, sorry, is called, the center spot is formed by electrons which penetrate through, that is the transmitted electron beam. Now related to the reciprocal space, if you double interatomic spacing in real space, what will happen in the reciprocal space? We know that in the reciprocal space, the diffraction vector has a magnitude of 1 by small d, that is the interatomic interplanar spacing. So if in the real space you have doubling of the interatomic distance, the spacing between the planes is, which is given by a by root h square plus k square plus l square. This will also double since a is doubling. So the in the reciprocal space, the spacing between the reciprocal lattice points will become half, right? So the reciprocal space will get compressed since the spacing is becoming half, and the diffraction peaks uh, will have half the spacing, which is the same thing. So answer is C. Um, for an FCC crystal, which is the first possible diffracting plane, we know that from the structure factor calculation, only those HKL planes which are unmixed will cause diffraction. So the answer is 100 is mixed, both odd and even numbers are there. 200 is unmixed, 111 is also unmixed, but this will be the first plane because this has the highest d spacing. So d spacing of 1 by root 3, a by root 3, and correspondingly magnitude of g vector is the smallest, is equal to root 3 by a. So because this is the smallest g vector, this will be the closest to the central spot and it will be the first diffracting plane, and answer is A. Next question regarding the diffraction pattern. We have already discussed this. The answer is that zone axis, the planes corresponding to a zone axis which is parallel to electron beam, will form the diffraction pattern. Now, when will dislocation contrast be visible? The answer is G bar dot be equal to 0. Sorry, dislocation contrast will be not visible if G dot B is equal to 0. It will be visible if G dot B is non-zero, that is G dot B, let's say, is more than 0. Next question. What is the reciprocal of a reciprocal lattice? Uh, so we know that the spacing in the reciprocal lattice is equal to 1 by d. If you consider points of, if you consider points corresponding to a plane HKL, then the spacing for them in the reciprocal lattice will be d star equal to 1 by d HKL. So if you again do reciprocal, you will again get the value of spacing in the real space between the lattice planes. So reciprocal of a reciprocal lattice, I think, should be a direct lattice, because and here also we are doing just a simple reciprocal, and twice of doing it twice will give you the same thing which you started with. Then some a question related to structure factor that gives you information about the so structure factor tells you about the intensity, the contribution to intensity due to the structure of the material for a particular HKL plane. So intensity, by intensity we can so by intensity we can say, just say that it tells you about the amplitude of the diffracted beam. The answer should be A. If you know small f atomic position XYZ, and then you also know HKL plane for which you are considering the structure factor, then you can get to know the amplitude of the exercise. Okay, same question again. Real and reciprocal lattice, they are inversely related. And d star equal to 1 by d NTM. Okay, so this is also a basic question. Correct answer is both can be used for imaging. Transmitted one will give bright field image, diffracted will give you a dark field image. Answer is A. With that, the assignment 5 is complete. And if there are any doubts, you can ask me now. I'll wait for 2 to 3 minutes. If there are any doubts, you can ask, else we'll wrap up and close this session.
Hello. Hello. Hello, sir.
Hello. Yeah, I can hear you.
Sir, for the final assessment exam,
Yes.
questions will be in multiple choice or as the theory part.
Uh, in the final exam,
Yeah. Yeah. As
I
like
think
assignment will be in multiple
hmm,
choice or on theory part.
I don't actually know about the assessment of this course.
Yes.
So, but probably in your portal, it might be given in the instructions. Or
Okay.
in case you are not able to get it from the portal, you can put it in the discussion forum. Maybe someone can just let you know. Yeah.
Thank
Okay. So, if there are no other questions, we can wrap up this session. Thank you for attending. I hope those who have missed this session, they'll be able to go through the recording of this session just to get a recap of the content taught in the week as well as a discussion of the assignments. So let's close the session now. Thank you for attending.
you. Sir, thank you.